Electrolysis of aqueous solutions involves using an electric current to decompose a substance dissolved in water, but the presence of water introduces additional complexity to the process. In an aqueous solution, not only are the ions from the solute present, but water itself can also participate in the reactions. Water, being a polar molecule, can dissociate into hydrogen ions H positive and hydroxide ions OH negative, adding another layer to the potential outcomes of electrolysis. When an electric current is applied to an aqueous solution, ions from both the solute and water compete to be discharged at the electrodes. At the cathode, where reduction occurs, cations move to gain electrons. However, whether the metal cation from the solute or the hydrogen ions from water are reduced depends on their relative ease of reduction. Often, hydrogen ions are more readily reduced than the metal cations, leading to the formation of hydrogen gas instead of depositing the metal. Similarly, at the anode, where oxidation occurs, anions migrate to lose electrons. Here, the choice between discharging the anion from the solute or the hydroxide ions from water depends on which species is more easily oxidized. In many cases, hydroxide ions are more easily oxidized than anions like chloride or sulfate, resulting in the production of oxygen gas instead of a nonmetal like chlorine or sulfur dioxide. To accurately represent the electrolysis of aqueous solutions, half equations are used to describe the reactions at each electrode. These equations show the transfer of electrons and must be balanced to ensure that the number of electrons lost in oxidation equals the number of electrons gained in reduction. For instance, during the electrolysis of aqueous sodium chloride, the half equation at the cathode might show hydrogen ions being reduced to hydrogen gas as shown on the screen. At the anode, chloride ions are more likely to be oxidized than hydroxide ions, producing chlorine gas, the formula for which is shown on the screen. In both equations, it is crucial to balance the electrons to reflect the conservation of charge. The total number of electrons involved in the reduction at the cathode must equal the total number involved in the oxidation at the anode, ensuring that the overall process is electrically neutral. Electrolysis of aqueous solutions, therefore, involves a delicate interplay between the ions from the solute and those from water. Understanding which species are more likely to be discharged is key to predicting the products of electrolysis. The careful balancing of half equations ensures an accurate representation of the electron transfer processes that drive these reactions. This balance not only upholds the laws of chemistry but also provides a clear picture of how electricity can be used to manipulate and separate the components of complex chemical solutions.